All right, so I did get a request in advance, and this was to go over the pressure dependence of reactions. So let's talk about this in two ways. One is just conceptually what we're trying to understand, and the two are the practical aspects of pressure dependence of reactions. So if we look at the rate law, R, and let's just have some generic rate law A, B. There are two terms to this rate law. The first K term, the pre-exponential factor here, is the probability they react. And it's not a probability unto itself, it's probability that these two molecules meet, it's a probability that the two molecules that meet will react. So it's the probability that these two meet, and this is the probability that they meet. So our concentrations here reflect the probability of these molecules finding each other. Now, the one on the left here we control with temperature, because the temperature basically supplies energy from the environment, provides energy to cross over the activation barrier. The question is, how do we change this? In A and B, the most obvious answer is to say you increase concentration. But the thing is, that isn't necessarily a practical thing to do. If you really think about it, going from 1 molar to 2 molar requires you to double the mass, whatever is being put in there. That's a high concentration barrier, and you may not necessarily want the product of those types of concentrations. So concentration here is how we're going to control the probability they react, which is what increases the rate of reaction. Now, for gases, we actually have a unique situation, because we can control the concentration of a gas the way you would control the concentration of liquid. You would just add more and more of the reagent. But another trick we can use is the pressure. So we take the ideal gas law, PV equals nRT. We rearrange. We'll get pressure over RT equals N over V. And these are units of molarity. So this will give us this component here. So for any ideal gas, not only can we control the concentration by controlling the moles, we can also control the concentration by controlling the pressure. Now, in the notes, there's a shorthand on how we make a conversion. But in order to get this, we can also use the mole fraction of species I times P naught, which is the total pressure. So mole fraction here, that's what we control by adding or subtracting reagent gases. P naught is the total pressure, so we can compress the system, and by compressing the system, pushes the molecules together, increases their likelihood they're going to react, and so this will increase the rates of reaction. Now, the fun thing about pressure dependence is that, I'll talk about it in just a minute, it actually can get you a lot more bang for your buck in terms of increasing the rate of reactions than just increasing the concentration alone. But to do this, we need to figure out the order of the pressure. Now, there's two ways to do this. There is the fast way and the slow way. The slow way you need to see, though, because it kind of explains where the fast way comes from. So let's say I have an elementary reaction. A plus 2B goes to C. And A here is liquid, B is a gas, and C is a solid. I don't know. We don't care about C. And we write our elementary reaction as R equals K, concentration of A, concentration of B squared. Now, the ideal gas law can only be applied to gases, as the name implies. So when we want to figure out the pressure dependence, we can only focus on the components that are gases. So to figure out the pressure dependence the long way, we use the substitution that the concentration of B is the mole fraction of B times the pressure over RT. And this is just the ideal gas law combined with Dalton's law to give us the substitution. So we plug it in, and we get K, concentration of A, mole fraction of B, P naught over RT, quantity squared. And if we start factoring things out, we'll get K, A, XB squared, R squared, T squared, P naught squared. So this tells us that overall there is a second order pressure dependence. So what does that do for us? Well, if I keep the concentration of A and B the same, but I double the pressure here, so I make this twice as big, it actually makes the rate of reaction 4 times faster because it's a square dependence. So I can basically quadruple the speed of the reaction just by doubling the pressure, which really isn't that hard to do in a reactor setting. So pressure dependence here is second order. Now let's say we make A a gas. So if A is a gas, now we have to use the substitution A equals XA, P naught over RT, and in here we get K, XA, P naught over RT. So now if I start factoring things out. I'll get a K XA XB squared. P naught times P naught squared is P naught cubed over R cubed T cubed. So this is actually a third order pressure dependence. If I double the pressure, the rate of reaction gets 8 times faster. So this is the long way to do it, and it's going to always work. It's going to actually start showing back up when we talk about equilibrium reactions in the next test. So how do we do it the fast way? Well, the fast way is just going to kind of pick up on a pattern here. So for the fast way, let's say I give you any reaction, and I don't specify what's a gas yet. So I would write the rate law out as normal. So that's step 1. Step 2, for the concentration of gases, you're going to substitute the concentration with the mole fraction. So let's say now A is the gas and B is a liquid. So this step we would get R equals K XA B squared. For the third step, we're going to add the moles of gas reagents and raise P naught over RT to that number. So, pause the video. So you add moles of gas of reagents, in this case we have 1, and raise P naught over RT to that number. That gives us P naught over RT to the first power, and that tells us we have a first order pressure dependence. Now again, this is just kind of a falling out of a pattern. If you repeat the concentration of whatever equals this mole fraction times P naught over RT, and you iterate this process over and over for all types of combinations, you'll start picking up on this pattern. Now let's say instead of being 2B, it's just 1B and they're both gases. If I follow this process again, I get K equals A times B. I'm going to substitute out the concentrations for their mole fractions. I have 2 moles of gas here, so that gives me raising it to the second power. So in terms of pressure dependence, it's a second order pressure dependence, and the expression is K XA XB P naught over RT quantity squared. Now, if you do it the first way, where you just do the little substitutions, that's fine. If you don't want to factor everything out, that's perfectly fine. You're not wrong by leaving this as XA P naught over RT times XB P naught over RT. The big thing is tweezing out the pressure dependence, and the pressure dependence you can figure out just by looking at the reaction. If you just add the moles of reagent gases in the reactant side, that's your overall pressure dependence. So hopefully that answered that question. But the pressure dependence, like the math is the harder part. Conceptually, it's not that hard. And we just kind of touch on it because we do emphasize a lot with this class about how the concentrations affect the rate of reactions. The pressure is actually kind of a clever little engineering trick. It's a lot easier to double the pressure than it is to double the concentrations. So if we just build a higher pressure reactor, that's pretty straightforward, and just hook a pump to it, we can make a reaction go much faster. And then when we start talking about equilibrium in the next test, we can start talking about how we can actually use pressure through Le Chatelier's principle to drive reactions one way or the other. So that's it for, rain's coming down really hard here. That's it for the questions I got in advance. Are there any questions from anyone who's watching right now? So I'm looking at the discussion board for the end of this week. It is actually covering the next material next week. So if you're looking at the discussion board, I think tomorrow, and it talks about defining entropy, enthalpy, internal energy, you don't have those notes up yet, feel free just to post for attendance. It's a pretty easy discussion board to do over the weekend. You'll find those definitions in the online notes. But there was no good way to stick this test midweek, so we're just going to see the test 3 material show up a little bit early. And I definitely know Monday's discussion forum, y'all are going to have a lot of questions for me. I find the test 3 material to actually be the hardest material for students. It is the most abstract in terms of concepts and the mathematics involved with it. That said, if you passed test 3 and you felt confident with test 3, test 4 is a breeze. Test 4 is a very simplified version of the concepts on test 3. Test 4 is acid-base chemistry. There's more definitions and more analysis, but the problems you have to solve are a lot easier. And then test 4, I think the hardest part is going to be the electrochem. Okay, so question just got asked, can you go over finding the activation barrier using a graph? And we're going to do it purely by graphical analysis. Or never. You will find online some people do a 2-point activation barrier. Do not do that. That is absolutely wrong. So in order to find the activation barrier, we need two things. We need to know the rate, the temperature that we took the measurement at, and we need the rate constant K. So we're going to have a series of temperatures like 25, 50, 75, 100, 125, and we'll have our rate constant K, and it's going to increase as a function of temperature. So I'm just going to make up some numbers. So the reason why we're having to vary the temperature is that our rate constant, assuming it's adhering to transition state theory, is going to take the form Ka to the EA, negative EA over RT. And this is the famous Arrhenius relationship. So this is what we physically measure in the lab, the rate constant K and the temperature. In order to find the activation barrier, what we want is an Arrhenius plot. And that's the ln of K equals ln of the pre-exponential minus EA over R times 1 over temperature. Should probably bring the video up to make sure you can actually see that. Yeah, you can actually see that. So what we have to do is we have to take our K data and take the natural log of all of them. And we need to get 1 over temperature, with temperature here being in Kelvin. So we need to convert this to 1 over temperature, and we need to convert this to natural log of K. And then what we're going to do is we're going to produce a plot of this data. So what I'm going to do, I'm going to bring up, I have to download it. So I'm going to download the data from the course website, and then we'll work the example for the homework. Just a minute. All right, so I've got the data up now. Bring it up the desktop. So what we need for Arrhenius plot is 1 over temperature in Kelvin, so 1 over Kelvin. And we need the natural log of K. So the 1 over temperature is 1 divided by that plus 273. We need to take the natural log of the rate constant K. And these are going to be our x's and y's. We're going to plot the data, so we're going to insert a plot. And you have to do a plot for this. You can't do it by hand. And the next thing I'm going to do is I'm going to add a trend line. So I've got my slope here as, or I've got my y-intercept as 8.4471, and I've got my slope here as negative 6527.6. So what I'm expecting to see is a straight line. Now, yes, I can generate this data myself, but even experimentally, and I've done these measurements experimentally, you do get a straight line. So your y here is your ln of k, and your x is the 1 over temperature. So if we look at it as y equals m x plus b, b here is our natural log of the pre-exponential, and our slope m is minus EA over the ideal gas constant r. So not only does theory predict a straight line, it tells us how we can take that slope that we measure graphically and the y-intercept we measure graphically and convert those to the pre-exponential factors and the EA. So for finding the pre-exponential factor, it's like you did for the first order plots. Your y-intercept is the natural log of what you're interested in. So in this case, your pre-exponential factor is just e to the y-intercept, e to the b. Now to solve for the slope in terms of activation barrier, we need to multiply both sides by negative r. So we're going to get that our EA here is negative slope times the gas constant r. And the r here, you have to use a very specific gas constant. So for our pre-exponential factor a, it's going to be the exponential of the y-intercept. For our EA, it's the negative of the slope times 0.008314. So this 0.008314, this is kilojoules per mole Kelvin. You probably also recognize this from the previous test. So 8.314 is kilopascals per mole Kelvin. Because of how SI units work, this is also equal to joules per mole Kelvin. I'm sorry, it's not kPa mole Kelvin, it's kPa liters mole Kelvin. So this is why we use the 0.08314, and this is why I encourage you to use it. Ideal gas constant 8.314, it's really only one number to memorize. So for this case 5 here, Our activation barrier is 54.27. You would round up to 3 sig figs, 54.3, and the same thing for the y-intercept. You'd round that to 3 sig figs, which would be 4,660. Now, the reason why we're going to do 3 sig figs for our answers here in the homework is not for ease. There is a justification for this. There are no rules for sig figs with exponentials. So if you take a natural log or an exponential, there is no way to take what we understand about sig figs and translate that into a natural log or exponential, which sounds weird, but there is a proof for it if you want to see it. So what we use is the rule of 3 sig figs, and this rule actually comes from slide rules. Slide rules have 3 significant figures, so back when they were doing these calculations by hand, literally 3 sig figs was all you could pour out the slide rules, so that's what we do today. But that's how you take tables of K versus temperature, and this is how you convert it to an EA. You convert the data from temperature versus K to 1 over temperature versus ln of K, make a graph, take the slope, multiply by negative R, take the number that you get for the slope and multiply that by negative 0.008314. That will give you the activation barrier, and if you take the exponential of the y-intercept, so e to the y-intercept, that'll give you the pre-exponential factor. And for all these, you should get an activation barrier between 25 and 150. That's pretty reasonable. And for the pre-exponentials, there is no reasonable range. That said, it's WebAssign, and I don't like coding in exponentials, so it's going to be something that you can enter in without an exponential. Looks like there's a mistake in one of my announcements. Let me correct that really quick. So for the pre-exponential, when you get that plot of K versus temperature, bring it back for you. So in this case, the y-intercept here is 8.4471. You just take the exponential of that value. So you take e and raise it to whatever the y-intercept is. And that'll get you the pre-exponential factor back out. Yeah, that was just a typo in the announcement. During the regular semester, it's set up so students can take it during the week. Yeah, you're welcome. Yeah, don't ever do a 2-point. Don't ever do a 2-point EA analysis. Textbooks teach it because the people that teach it have never done it. And you'll find this with textbooks. You can tell when an expert wrote it and when they didn't. So the Arrhenius plot has a lot of advantages to it. So you kind of saw this with when you were doing the data analysis and trying to find K, that you got different values of K depending on where you looked at the slope. And you'll see this with real experimental data, and I've embedded some noise in your homework as well, that each of these kind of give a different slope. And so depending on where you take your 2 points, you will get a different activation barrier. What you really want to do is you want to average across a whole bunch of points. So your average line, so your line fit is basically going to be an average of slopes. And so off the bat, if you've got all this data, you might as well just take a line and go through it, because this is going to create, it's going to average out errors. Points where K was higher or lower than it should have just because of experimental error. So off the bat, you want to do it because it averages out errors. The second reason you want to do this is if you just do a 2-point interpolation, you've got no statistics. You don't know how precisely you know that number. In Excel, there is the line est function. And not something you need to know for this course, but it does pop up when you start doing analytical chemistry. So I'll switch to the desktop. So the function line est lets you actually get statistics off of any type of linear regression. So see here, I've got the slope as minus 6.52762. It has it here, and that's the y-intercept. But the big thing here is that it's going to give, so let me go ahead and convert this to EA. It's negative of that times. So what this is telling me is that the activation barrier is 54.27064, but the number beneath it, that's 332, that's the uncertainty in the slope. So it's 54.27 with an uncertainty of plus or minus 2.8 kilojoules per mole. So if you just do a 2-point interpolation, you can't get any statistics off of it. You don't know how reliable you know that number. So first argument, why you would never do 1-point or 2-point interpolation. You don't know the reliability of those 2 points, so if you do multiple points, you get an average that's much more accurate. 2, because you're just doing 2 points, you can't get statistics off of it, which means you don't know how well you know that number. Even with this data, like there's a plus or minus 3 kilojoule error. That's quite substantial. And then far more practical in terms of experiments is that you don't know if the rate limiting step changes. So if we take an Arrhenius plot and we get something that looks like this, we have 2 slopes. And what's happening here is that the rate limiting step has changed. So whatever the mechanism is, RLS can shift. And this is something that is known. It's a common experimental phenomenon. So let's say you take the number here and here, you're going to get an EA, but you don't know that at this point, somewhere in this range, the mechanism is changing. And let's say you really measured these 2 points. Well, the EA you're getting is completely off because it doesn't match either EA. So that's another thing, is that if you do a 2-point, you're making a huge assumption that the mechanism stays constant on that range. If you happen to just be unfortunate, which does happen, you can be straddling 2 different regimes of the reaction mechanism and have an EA that's complete and utter nonsense, because you're either getting this, you're getting both this EA wrong at high temperatures and you're getting this EA wrong at low temperatures. Or other way. EA is going to be, EA at high temperatures is wrong and the EA at lower temperatures is wrong. So I understand why your book does it. The practical reason why people do that is because that's easy to do in a lab setting. Take your reaction, run it at room temperature, put it in ice water, 0 degrees C, run it and go, oh, what's the 2-point EA? The problem is that that teaches you the very bad habit of thinking that you can do a 2-point interpolation to get the EA. It is never, ever, ever done that way. You would always build an Arrhenius plot. Honestly, you'd build an Airing plot, but you would build a plot and do that because it's going to average out a lot of errors and it'll give you a lot more insight. So does it work in all cases? I would say it works basically in none. Yeah, you're welcome. And I'm glad you're saying that, like, it's a lot easier. It's like, yeah, take your case, take your temperatures, plot it, and you're done. We used to have this awful thing in our lab manual where somebody actually went through and like derived the algebra for a 2-point interpolation, and it's this big nasty natural log exponential equation. Like, I get why you did that, because yes, for students, you've got k1 equals a e to the minus ea over rt1, k2 equals a e to the minus ea over rt2, and so you take the ratio, actually take the natural log of both. So you get the ln of k1, ln of a minus ea over r1 over t1, ln of k2 equals ln of a minus ea over r1 over t2. You subtract the two equations and you get ln k1 over k2 equals minus ea over r 1 over t1 minus 1 over t2. And if you rearrange, you'll get that the ea is r ln k1 k2 all over 1 minus t2 minus t1. And you'll get this big nasty equation that you can do, or you can just do a linear regression, which is a lot easier. So again, I understand why people teach this. It's because it's something that's doable in a lab, but again, there is no way to do the, well, there is a way to do uncertainty, but it's nasty how you do the uncertainty on that. Like, oddly, the right way is the easier way in this case. Again, when we're in seated, the seated lab, we actually do the 4 temperatures and we make you do the Arrhenius plot. It's an kind of lab. It doesn't really give you good data, but it does let you go through the process. It's just something you can't do at home, because we have 40 and 60 degree water baths that it's about a $2,000 piece of equipment, maintains the water. We actually borrow it from biology. But yeah, you do 0 room temperature, 40 and 60, do the Arrhenius plots, and you do get an EA. Typically, it's a reasonable EA. And it's actually a variation on the iodine clock lab that you do at home. So with that lab, we actually tell you what the orders are, and we make you work out what K is. Correct. And for the exam, you'll be given a graph. So this is definitely one of those exams where the homework is a lot harder than the actual exam, because the one thing I can't give you an exam is a computer to go through and calculate it. But it's one of those, I also don't want you getting in that really nasty habit of thinking that you just measured ln to k versus 1 over t in the lab. So definitely I can tell you, for this particular problem where you're asked to find EA, you're going to be given the Arrhenius plot. And now it's up to you to interpret the graph. So you're given the graph in a linear regression, up to you to make sense of what those numbers mean and give me a meaningful answer. But this class, definitely for this one, the homework is a lot harder than the exam. I can't make you draw plots during an exam. It's just not practical. But I would hope that after building the Arrhenius plots, after building the concentration versus time graphs, you begin to intuit what these graphs are telling you, and then the exam ends up becoming very easy. That said, I do give students fair warning on this exam. It's a pretty binary exam because of that. So with an Arrhenius plot, you've got ln k versus 1 over temperature. And I give you the plot, the y equals mx B. So all the work's been done for you. Here's the problem is that if you don't know how to do anything with this, there's no room for partial credit because you have to know what these terms refer to and how you get an EA out of it. So if you just write a slope, that's not correct. So this test ends up being a lot more binary in terms of the grading. There's a lot of A's, there's a lot of F's, and there's not really that much middle ground. But if you understand the material, this ends up being actually a pretty easy test. Yeah, method of dimensional rates, graphical analysis, EA, and there's one other plot that you have to work with. But yes, I run you a lot for the second exam in terms of the homework, so you have a very trivial second exam. The third exam is the hardest because it's the most diversified in terms of what it talks about. There are 3 concepts that we're going to have to cover over test 3 and test 4: equilibrium, thermodynamics, and acid-base chemistry. The 3 are all connected. So it's one of those, like, you just kind of have to find a place to start and work from there. And because it's the first part of 3 concepts that all have to be understood in parallel, there's a struggle there. But definitely with the next exam, if you can do the thermo and you can do the equilibrium, the third part, the acid-base chemistry, falls right into place. Yeah, I've actually had students turn in their 4th exam, like their hands shaking because they were paranoid. The last problem is either very easy or very hard. If you know what you're doing, it's a very easy problem. But they turn it in like, I solved this in 3 lines. It's like, yeah, it's about right. Like, well, I just thought there was going to be more work. It's like, no, about 3 lines is all it takes to solve the last problem. But then I've definitely watched people chase their tails in the last problem because they didn't really understand the concept. And like, it's unfortunate. Like, I want you to succeed. Like, as instructors, we do want you to do well and we do want you to succeed. Hopefully you're going to see with my exams, there's no gotcha questions. Like, I'm not going to put something completely out of left field on any of the exams. But particularly with online, it's hard to assess if you're understanding it for the right reasons. It's something I can gauge a little bit better with in person by walking around and asking you questions. But definitely the 4th test, like, the last question looks super hard, but if you know how to set it up, it's really 3 lines and you're done. In this exam that's coming up, like, if you understand the concepts, like, a lot of this is going to be a very fast exam. Because it's like writing elementary rate laws. Like, if you know how to do that, like, you can just you can pop them out really fast. So we'll see. You may all disagree and say, like, these exams are incredibly hard. I don't know. So, so side products are more just kind of setting up that idea. We write these nice ideal reaction mechanisms. So we can write something like platinum catalyzed combustion of hydrogen and oxygen. And this is more setting you up for if you go on to organic chemistry. We do talk a lot about undesired side products. balance it out. So this is a nice simplified version of hydrogen oxygen combustion over platinum. But the thing is that this isn't the only thing that happens. We can also get this reaction where we have two platinum oxygens to give us peroxide on platinum. And what will end up happening is that because we have these oxygen and monatomic oxygens and hydrogens, they can actually come together to form hydrogen peroxide. Now, generally speaking, you're not going to get a lot of this, but you do get a small amount of peroxide when you do these types of reactions. So we would consider hydrogen peroxide a side product or undesired byproduct of hydrogen oxygen combustion. Now, the thing is that if you don't know any of these details, so if you don't know anything about the mechanism, it's really hard to see how H2 and O2 can give you both that, as well as a small amount of H2O2. So this is just kind of setting you up for organic chemistry. Organic chemistry is going to focus on mechanisms a lot more. You're going to start breaking down like how reagents go to products. But because you have these intermediate steps give you areas where things can go wrong. You get undesired side products. In this case, it's peroxide. By organic chemistry, you could be trying to make an alcohol and you end up making an alkene. You go to make an alkyl halide and you end up getting multiple substitutions. And seeing the mechanism gives you a feel for where things can go wrong. In this case, we do have hydrogen and oxygen. So if we run in a really oxygen-rich environment, we may end up generating a large amount of these peroxide groups on the platinum that react with the hydrogen. If we go to high amounts of hydrogen, so we keep the oxygen concentration low and the hydrogen concentration high, we're more likely to get rid of those peroxides. It becomes a design consideration and a reaction consideration. But again, we're kind of just introducing reactions here. We talk about side products so you're familiar with the word. If you go into organic, we talk a lot more about this. But you can't understand side products without understanding mechanisms. Or you can't really do anything. You can't really see where side products come from without seeing a mechanism. You're welcome. It's a good question. You're welcome. I'll see you probably tomorrow. I think DU is the last concurrent viewer. So those of you who are watching this video, I'm going to guess that there's probably not a lot of people that ask questions in these last 10 minutes. I'll keep the video up, but I think it's probably just going to be me for the rest of this time. thanks. I don't really know. So you can definitely tell when you get towards the end of those units, I have no idea about biological molecules. It is definitely not my background. But thanks for the encouragement. There's definitely one or two of those videos I need to correct. There was one that a student did point out, like, I did something very wrong in the video I should have caught. But yeah, thanks. And any feedback you have for videos I should post or anything that needs clarification, please let me know. All right, so that's kind of the end of it today. Again, if you ever have questions, please feel free to email them to me in advance, and I will try to answer them at the start so we don't sit through the whole video. And I will see you all tomorrow.